So we're recording now. So I'd like to begin today's lesson by briefly going over some things you learned about linear equations. And I taught many of you in year 10 last year. So you will have seen these ideas before. So the idea is, given 2 points, find the equation of the line. And from your quizzes, it was clear that you'd forgotten, which is okay, because I understand. So there's two cases we want to consider today. The first case is where this thing called the y-intercept is provided. So we're setting this up so that you always have two coordinates, and once you've got 2 points, they uniquely determine a line. So here I've got 2 points, 0, 20, and 10, 150. And I want to write down an equation, y equals a plus bx. By way of reminder, a is the intercept, and b is the slope. Another word for slope is gradient, which is what you used last year. So looking at this linear graph here, we can see that the y-intercept is 20. So that is when x equals 0, y equals 20. There was no need to do any calculation to find a. You simply had to read it off the graph. So I'll break it up into steps for you. So step 1, read off the intercept. Step 2 is to calculate the gradient. So if you've forgotten, if I have 2 points with coordinates x1, y1, x2, and y2, then the gradient, or the slope, which we will call in this course, is given by the change in y, y2 minus y1, divided by x2 minus x1. Change in y over change in x, or rise over 1. So once we have that, I can substitute these values, 0, 20, 10, and 150 into this formula, and we will get the following. So it is good practice to write the formula, so we can do that. And in this case, I substitute the values in. So we've got the intercept, we've got the slope, and those are going to be the two numbers, a and b, in my equation y equals a plus bx. So our final answer to the question involves stating the equation. So I can write y equals 20 plus 13x. Notice that I've replaced a and b with the numbers that I calculated in the question. When you do the exercise 7D, there are quite a lot of questions where you are given the line and they ask you to find the equation. So this is the simple case where the y-intercept is given. Do we have any questions? Can you just give me a nod if you're following this? Okay. Yes. Are you going to put these on? Yes, this will go on Teams right after this lesson's over. Yeah. Should I move somewhere else? Yeah. who's still writing? Yep, how much more time do you need? Make sure you've labeled the points. So this example applies to this very specific graph where these are the values, yeah? So yes, I think put the picture in. Yeah. So while we're waiting, I have seen Year 12 exam questions where they give you the line and they say find the equation. It's actually not taught in Year 12, so there's no time to review linear equations next year. So you have to learn it this year because they assume that you know it next year, and they have in the past tested it. So maybe in the interest of time, if you haven't got everything down, I'll just upload the notes when this is over, and you can go back and fill it in, because otherwise we'll be here for a long time. So let's keep moving. Sorry if you're still writing. Okay, here's another example. Now, there is a trap here. We cannot assume that the y-intercept is 100. Can anyone tell me why we can't say a equals 100 here? That's right. So the most likely scenario next year is you'll deal with a graph that looks like this. It doesn't pass through 0. You're given a box rather than 2 arrows. And we want to be able to find the equation of this kind of line as well. And the approach is different. In the last example, we just wrote down the intercept. Here, we actually need to find the gradient or the slope first. So here, step 1 is to calculate the slope. So again, if it helps, label the information of x1, y1, x2, y2. And our formula for the slope is y2 minus y1 divided by x2 minus x1. And as you're looking at this picture, you should see that as x increases, y decreases. So I'm expecting to get a negative number when I finish this calculation. Okay, so it's a bit messy, but that's okay. All right, so now that we've got the slope, our next step is to find the intercept. So here what we want to do is substitute b into the equation y equals a plus bx with one of the coordinates. So it actually doesn't matter which one you use. You can use the first one or the second one. I'll just use the first one. So we know that when x equals 20, y equals 100. So therefore, I can write the following. 100 equals A, which I don't know, plus B, which we found, times X. So you don't have to write that first line there, y equals A plus bx, but I'm just showing you that we have substituted neg 3.75 here. Okay, so that's B. And in a different color, I've used 20 and 100, and I've replaced those numbers here. And what we're doing here is we are solving for A. So over here, I've got a linear equation in terms of A. So once I do some rearranging, I will be able to write down A equals some number, and then I've got the intercept. And once I've got the intercept and the slope, I can write down the equation. Y equals bx. Okay, so I'll leave it up to you to decide how you want to do this. But I believe it is going to be that. And so A equals 175. Okay, can you give me a nod if you were able to follow that, please? Okay. Would you like to ask a question? If there was something that you didn't follow. All right, that's okay. So this is why I'm going over this again. So let's start with step one. Find the slope. Is that okay? So the reason why people have trouble with this calculation is because there's a few steps involved. So here we start by finding the slope of the gradient. And that just involved applying this formula. Is that use the gradient or the slope formula to find the steepness of the line. Once we found the steepness, which was this number, I'm not done. Because in order to finish this question, I need two numbers. I need to be able to write down y equals a plus bx, with a and b replaced with numbers. So we found b. Therefore, I'm going to need to do another calculation to find a. And that's what the second step is about. So what we did was, I said, okay, I know that y equals a plus b times x. That's the definition of a linear graph. We found b, so I know that. And I also know a value of y for a particular value of x. I know that when x equals 20, y equals 100. So I can replace x with 20 and y equals 100. And now I'm left with an equation that only has a in it that I can solve. And then this b also. So I've got b, got a, and now I have both numbers.
straight up, or should we do it later?
No, I just didn't know what we were doing. Like, once I look at it, I know
Yeah.
what we're doing.
Okay. All right. Sorry, I misunderstood. So we haven't actually answered the question, so let's make sure we do that. So step 3, I want to keep it all on one page. So step 3 is to write the equation. So just put it all the way here. So y equals 175 minus 3.75 x. Okay. I've replaced a with 175. I've replaced b with negative 3.75. There are lots of exercises in this set that require you to do this. So, because we don't see each other again until next term, just send me a message over the holidays if you need help with this. Okay, if you haven't written everything, I will give this to you straight after this is over. But let's keep moving. Okay. This is one of the high points of the general maths course. So in any field where you generate numerical data, whether it be science or business, whatever you like, we ask the question, is there a relationship or an association between two numerical variables? And the simplest thing that we can do with that data is to try to make a model, to make predictions. And there are many possible graphs that we could use. The simplest one involves a straight line. So here I present the problem that we are going to solve today. If I give you a bunch of data points on a scatter plot, can we find a linear graph, y equals a plus bx, that models the data? And I'm going to present to you the theory of how this is done in sort of a standard way that the statistics and mathematics community uses very commonly. So in order to do this, I need to define something called a residual. So I want you to think of this as firstly a scatter plot with 4 dots, 4 points of data, and in green I've drawn a line, a linear graph. I haven't told you how to draw this linear graph though. So right now I could have drawn this graph or this graph or this graph. It's not clear which one is the best at this point, so that's coming soon. But for now, let's assume that we have picked a graph, and what this graph is going to do in green is it makes a prediction. This is the key word for us today. The green line makes a prediction for y at each value of x. All right. The next thing I want to say is you will notice the predictions are off. There's an error everywhere. So if I think of these dots as the predictions made on the line, there's a gap, which I've drawn in red. That's kind of like an error. So if I think of the blue dots as the original value in my data set, and the green dots as the prediction that's made by the line, there's a difference, there's an error. They're not the same. You can see that from the picture. So we're going to define the residual value to be this error or this difference. Okay. So the original value in the data set is, these are the dots. So I'll say these are the dots on the scatter plot. And the predicted value is the value on the line. Let me reassure you that it takes some time to fully appreciate what is on this page. So I'll go over this again next term, but I want to introduce it to you this way. So this is a definition. So residual value equals the actual value minus the predicted value. Okay, do we have any questions about this page? You okay? All right, so the key idea here is the dots are the original data. The line, which we haven't chosen yet, the line's going to make a prediction, and there's going to be a difference between the prediction and the original value. We call that difference the residual value. Keep that in mind. All right, here we go. So you don't need to copy that again. That's the same. That's the same. That's the same graph. So, all right. So here's some theory. The linear least squares regression line. Now that's a bit of a mouthful. Is defined so that, and here's the property, the sum of the square of the residuals is as small as possible. Next year, you will be expected to know that. So I'll just give you a few moments to get that sentence down, and then I'm going to discuss that in the context of this graph here. Okay, so you don't need to write this. You can look at it later. So what I'm going to define is 4 coordinates: x1, x2, x1, y1, x2, y2, x3, y3, and x4, y4. If you choose to write this, do it on a new graph because it'll crowd out the original graph. And then in green, I'm going to give a y value to each prediction. So I'm going to call the predicted values y hats. There's no agreed way to do this. So what I want you to note is that the x values are the same, but the y values in green and blue are different. So the original values I'm going to call y1, y2, y3, and y4. Those are the values in my data. And then the predicted values for the same x value according to my graph, I'm going to call y1 hat, y2 hat, y3 hat, and y4 hat. So according to our definition for the residual value, I'm going to use the letter E because R is taken already for the correlation coefficient. So on the previous page, we defined the residual value to be the original value, that is the actual value, minus the predicted value. So it's going to be y1 minus y1 hat. That's this red arrow. So essentially what's happening here is I'm calculating this difference 4 times, once for each data point. E1 and E3 are positive. I won't write this. So from the picture, you should see that sometimes the points are above the line and sometimes the points are below the line. So the residual could be negative if the original value is below the predicted value. Take away a larger value, it's negative. So sometimes my prediction is going to overestimate the data points, and sometimes it's going to underestimate the data points because the lines will run. So once I've defined these residual values, now I'll tag this here. What are we trying to do? I think in the ideal world, you would agree with me that all the points would lie on the line. But that's not going to happen. So intuitively, we want these residuals to be as small as possible. Is that something reasonable to say? We want the line to be as close as possible to all the data points. That would make it a better fit. The problem is I'm always going to have some errors for these residuals. So I know I have to deal with them. So somehow, if I add up all the residuals together, I want that total difference to be as small as possible. And that's what this criteria is for. So instead of adding up the residuals, what we actually do is we square these residuals and then we add them up. And there's some mathematical reasons behind that, which I can show you later. So I would like you to write this down. So we choose A and B. So remember, y equals a plus bx. We choose A and B so that e1 squared plus e2 squared plus e3 squared plus e4 squared is as small as possible. So again, if you're not following every detail, that's okay. It didn't happen in my last 2 year 11 classes. The idea is if you've seen it once, it's easier the second time you see it, and the next time will be next year with a different teacher. So, here's our goal. If I choose a line, y equals a plus bx, I will have these errors or these residuals, and I want these errors to be as small as possible when I calculate this particular sum. If I can make this as small as possible, then I have chosen my slope and my intercept. Yes?
So were you doing this in year 12, like we're not doing a test or this in year 11?
I will put some bonus questions on the test because I want you to learn this. You won't have a lot of time next year because it goes quite fast.
When do we have our next test?
Huh?
When is our next test?
Your next test will be in the second week of term 4. So we'll have a week to sort of finish the last exercise, and I'll give you a practice test before the real test as well, because it's a hard topic. Okay. I'm going to do it the other way, so add another page. Okay. All right, so if you fell asleep, you can wake up now. So now here's an important part which you need to know. So if we minimize the sum of the square of the residuals, so that's the e1 squared plus e2 squared, etc. On the previous slide, I set up the problem. When I choose my line, I want to minimize the sum of the square of the residuals, but I didn't give you a way to do it. Because there's a million different possible lines I could draw, different intercepts, different slopes. So this actually becomes a problem that needs to be solved, and it has been solved. So we just need to know the formula, essentially. You need to know the theory of what we're trying to do, and you need to know the formula which falls out from the theory. So here it is. The slope is defined by R, the correlation coefficient, which we met last lesson, the standard deviation of y and the standard deviation of x. The intercept, a, is defined like this. It's the mean of y minus the slope we just calculated times the mean of x. So my claim is, and I know I haven't proved this or justified this, that if I do this, if I minimize the sum of the square of the residuals, then there is one and only one choice I can make for A and B, and it's that. And so when you use your calculator most of the time to fit a straight line to your data, that's actually what it does. So now there are two cases. Case one is where I just give you the summary statistics and you have to use these formulas. Case two is where you get the raw data and you do it on the CAS. So I think we should do both. So I think we will start with an example involving the formulas. I'll write the formulas down if you haven't got them. So B is R sy times Sx, and A is y bar minus bx bar. And here we're doing an example. Calculating the least squares regression line. From summary statistics. Yes? Gotta go? That's all right. So this will be uploaded to YouTube later. Okay, no worries. Okay, so here's the setup. So suppose I tell you that R has some number and my prompt for you is to find the equation of the linear least squares regression line.
When did we work out that I was 0%?
So this is a really good question. I haven't given you any data. There's no scatter plot. I have said, suppose I have a data set where these are the statistics. Okay, so someone has calculated these already, and with just these statistics, I can get the line. Okay? In the next example, we'll do it with all of the data. Okay? So we need to know both. So this question is actually quite straightforward. You don't even need to know the theory. You just need to know these two formulas and then apply them. So first, we'll start with the slope. So B is R times Sy divided by Sx. But I know R, Sy, and Sx, they were given in the question. So here, it's going to be 0.74 times 3 divided by 2. And that is 1.11. Yeah, just check that. Okay. Can anyone tell me why I've calculated the slope first rather than the intercept?
Because you need the slope.
Yeah, so have a look here. The formula for A depends on B. So if you try to calculate A first, you run into this problem where you don't know B. So when you do this, we've got to calculate B first. Okay, for the intercepts, the formula is A equals y bar minus B times x bar. And again, it's a simple matter of substituting the numbers that we were given. So y bar was 20, B was 1.11, and x bar was 10. Okay. So using two simple formulas for A and B, I've now got my slope and my intercept for this thing called the linear least squares regression line that minimizes the sum of the square of the residuals. You'll memorize that soon. Don't forget to write an equation as your final answer. So y equals 8.9 plus 1.11 times x. Y equals a plus bx, where a is your intercept and b is your slope. Okay, I think we're almost ready. So I think I just need to do one more example with you.
This issue with the standard deviation.
Yes.
We can only find that from the cats.
Yes, that's right. So that's right. So I think once I do the next example, this will answer your question. So um, here, I gave you the standard deviation. Most of the time, what's going to happen is you'll get the original data and your calculator will spit out A and B for you. So there'll be no need to do this calculation. The only time you need to do this calculation is if you don't have the original data and you are only given the summary statistics. Okay? So perhaps the next example that we're going to do is the most common case. So here we go. So I need to make up some data again. So for this one, you'll want to get your CAS calculators out because we will put this data into a spreadsheet. Okay, so take a moment to type the data in. I've only got one screen, so I'll need to photograph this and type it in. So I'll put this to one side so that you can still see the data. Then I'll show you the CAS calculator on the other side.
What was on B say?
B? Well, it's not finished yet. Okay, so we can say 190. Predict weight when height is 190. Okay, so we can see both now. So new document, lists and spreadsheets. Remember to give your data a title for each column. So I'll call height and weight. And then gradually type your data in. All right, just give me a nod once you have all the data in. You don't have to do anything yet with the menus. Okay, so we have done this many times. So it's menu, statistics, stat calculations, and number 4, linear regression A plus BX. Now, I haven't told you which one is the explanatory variable. I would have to tell you in an assessment. So for our purposes, we will use height. Height as the EV and weight as the RV. Okay? So you'll notice A plus BX, and the calculator has given us A and B. Notice we did not need to use the formulas, and the reason for that is the CAS has already done the calculation for us. So the only time you need those formulas is if you don't have the original data. Most of the time, you will actually do this, but I want you to know the formulas as well, because you need them next year. Okay, so if we go back to the question, I'll say using height as the explanatory variable. So remember, a linear equation looks like this. Y equals A plus B times X. Now, the explanatory variable is X, and the response variable is Y. The convention that's used in this course is if I have worded descriptions of my variables, I'm going to write my equation with words. So height was my explanatory variable, and therefore the other one, weight, is my response variable. So I'm actually going to write this equation with the word weight. And, there'll be rounding requirements sometimes, but I'll just use some sensible values. So weight equals A plus B times X, which in this case is height. So I'll write a note for anyone who's reading this later. Use spreadsheet analysis. Scroll up.
Yes.
That? Yeah. Sure. So we used spreadsheet analysis, linear regression, a plus bx to get a and b. All right, so now that we've got this equation, how do you think we might predict? So notice that word again, predict. I used that earlier. How might we predict the weight of someone who has a height of 190 centimeters just using this data?
Substitute 190 for the equation.
Yeah, for which variable? Weight or height? Yeah. So we're saying height equals 190. And that is going to define a value for weight. All right, so you will get a question like this. So we'll substitute height equals 190 into the equation that we just calculated. So when we do this, we get weight equals negative 39.5 plus 0.633 times 190. And you'll need, I'll need a calculator for this one. I can't do this one in my head. The number?
8.77.
Thanks. Okay, so in the test, I tell you how much to round it to. Here, I'm more concerned with the method rather than the actual answer. Let me take a moment to show you what we've just done. So if I go back to my CAS, so I'll say I'll do Control I. You don't have to do this. Control I, data and statistics. I can make a scatter plot with height as the explanatory variable and weight as the response variable. So the data it doesn't look exactly straight, but the simplest model that we could possibly fit is a straight line. So that's our starting point. So we can fit it here as well. Menu, analyze, regression, show linear. There's my equation. Those numbers should look familiar because we just calculated them. My last data point is at 180. So what we've done is we've said, okay, let's assume that this relationship continues for other heights. I haven't got anyone with a height of 190 in my data set. But let's pretend or assume that this general pattern continues. If it continues and I extend this line up till 190, what will the height be? That's what we've just done. We've done a prediction. So this idea is often used to predict the future in sort of financial or population contexts as well. So if you've got data, what would happen if the general pattern continued? What would I expect? So we did it with height and weight, but this can be done with any numerical variables that you like. And of course, there are some dangers in assuming that the pattern continues, but it's a very simple prediction that we can make with data. And if you don't have data and you want to guess, you use the data that you have and then make a prediction based on that. So that's why this technique is so powerful, and that's why I think this is perhaps one of the high points of the general maths class. Okay. Just quickly looking at the book, we've actually done everything that we need. The only other thing is sometimes they ask for the correlation coefficient, and there's no need to do any additional work because the correlation coefficient is R. The CAS already gives you that. Please note it's not R squared. R squared is something different. You'll learn about that next year. So remember, correlation coefficient is R. So you don't need to title it that. So R is the correlation coefficient. See notes from previous lesson. Don't use R squared because that's different. Common mistake that students make. They see R squared and they think that's R. It's not. And holiday homework. So I'm not going to assign the next exercise, 7E. I'm only going to assign what I've covered today, which is up until the end of 7D from the work program. So you are all here. So I expect 7D to be done when you come back, and I think I'll quiz you on the first day back. Okay? To make sure that you've looked at it and yeah. And I'll check your books as well. All right, you've been great. Thank you for your patience during that long segment. So the formal part is now done. I'll show you where the formula comes from at the end, just for fun. But now you can continue with your work program. And I'll take any questions you have as well.